Okay, so after watching this video lecture, students will be able to differentiate between first, second, and zeroth order reactions with integrated rate laws. Students will be able to utilize graphical data to identify the reaction order, as well as manipulate the equations to determine time, concentration, or the rate constant associated with each of the integrated rate laws discussed above. In our last lecture series, we were looking at rate laws that look like this. And basically, the rate law that we have written here is known as a differential rate law, and it relates rate to the concentration of your reactants to some power. Now, these are useful. We know how to use them and obtain data about our specific reaction rate from our experimental data. We've looked at these. However, today what we want to talk about is integrated rate laws. Okay, so why would we want to use integrated rate laws? Will relate to the concentration of the reactant as a function of time. Okay, so it'll give us some additional information. Now, integrated rate laws obviously are going to be utilizing calculus to establish the equations associated with these rate laws, but you guys will not be expected to do any of the calculus. All that's expected of you is to know the actual formulas for the rate laws themselves. Okay, so integrated rate laws can be first order, second order, and zeroth order, and we will talk about each of these. Let's go ahead and look at first order reactions. Okay, we know that this reaction here is a first order reaction because our rate law tells us, because our n equals 1 according to the differential rate law we have written here. Now, we know that when we double the concentration for this reaction, we're going to double the rate of the reaction. Now, if we were to integrate this, we would get the following equation. Okay, so we have this equation here. Okay, so this is for a first order rate law. This is the integrated version of a first order rate law. And what you have is this form. You guys need to memorize this formula here. Obviously, this concentration value and this concentration value is going to refer to the reactant that you're looking at. In this specific case, there's only one reactant, so that's what we have plugged into here. And I want you guys to notice the sub T and the sub naught here. Okay, the T here is going to correspond to the concentration of our reactant at whatever time we're analyzing. And in this portion of the integrated rate law, the sub-zero associated with the concentration here is going to be referring to our initial time for this reaction. Now, again, we have another T here that's also representing time, and of course our K is our rate law constant. So this is your integrated rate law for first order reaction. Okay, make sure that you memorize it because this is the kind of equation that you will be utilizing. Okay, so let's look at the usefulness associated with the integrated rate law that we see here. The integrated rate law that we see here is obviously a first order integrated rate law. So basically some things that we can figure out using this rate law. Okay, so we can figure out the concentration of a reactant remaining at any specific time after the reaction has started. Okay, if we know our initial concentration of our reactant and the time frame we want to analyze at, obviously we can analyze the concentration at that specific time frame by manipulating this equation. We can also figure out basically the time required to basically have a specific fraction of a reactant remaining in the sample. Okay, and we can also figure out the time interval required for a reactant concentration to fall to a certain level. Okay, so if we know our values here, we can figure out how much time that's going to take. So this first order integrated rate law has a lot of information because it has both a time and concentration component that we can basically manipulate and obtain information from. Okay, so let's go ahead and let's look at our integrated rate law in this generic form. Okay, so some things to note about this is first of all that our concentration is going to be dependent upon time. We can see the time relationship being directly proportional to our concentration of our substances. Or reactant rather. Okay, also another thing to notice is that if we relate this equation to our y equals mx plus b equation, we can see that our y would correspond to the ln of our concentration of A. Our slope is going to be related to our negative value of our reaction constant, and of course our b value is related to ln of a. But if we were to go ahead and take data such as concentration and time from, let's say, an experimental procedure, and we were to take the natural log of our concentration and put that as our y-axis and our time as our x-axis, if we have a first order reaction, we will get a straight line with a slope of negative k, right? So what we will see here is that when we graph first order reactions, first order integrated rate laws, by taking the natural log of our concentration and our time values, we will get a straight line. Okay, now this is a way that we can check and see if we have a first order reaction. We can take the information and graph it in the manner that we just discussed, and that will help us determine if we have a first order reaction or not. Okay, another thing that we can do here, obviously, with the equation is we can manipulate it, and of course, as we talked about a little bit earlier, we can relate the concentrations of our reactant at a specific time versus the initial value, and we can see how that ratio is going to change over time when we do these manipulations. Okay, so first order reactions, we're going to have this negative slope with the graphing of ln of our concentration versus time. So make sure you guys memorize that and have that in your heads. Okay, so we're going to be looking at the decomposition of N2O5 like we have in previous slides. And we know that the rate associated with this process is first order. So our integrated rate law for this first order reaction is going to look like this. Now, let's say that all we had was the data associated with this, but not necessarily the rate that was established from a previous experiment or what have you. All right, a way to ensure or to verify that this is in fact a first order process is that what we would do is we would take the concentration of our N2O5, take the natural log of each of them, and graph them along the y-axis versus our time along the x. And if we get a straight line with a negative slope, we have our first order reaction. Okay, so when we do that over here, what we actually get is that straight line with a negative slope. So that tells us that we have this first order reaction with respect to our N2O5. Now that's one useful tool or one useful way that we could use this graph. Okay, another useful way that we could utilize this graph is, and the data we've been provided, is to actually solve for our rate law constant. And in order to do that, we're going to have to isolate k. So if we go ahead and we manipulate this equation, we end up with the relationship between our concentrations at the initial and some time we want to look at. And obviously we have our t component over here, our time component. So then we need to isolate that out. So we're going to divide out by negative t, and that's going to give us k all by itself. So now that we've isolated k all by itself, we're going to go ahead and plug in our concentrations and the corresponding time. Okay, so what we're going to use time 0 all the way to time 400 seconds. Okay, so we're going to use those two corresponding concentrations to plug into our values. Once we've done that, we're going to take the natural log of the ratio between our concentration at time 400 and our concentration at basically time 0 and divide by negative 400. That will give us 6.93 times 10 to the negative third inverse seconds. Okay, and this is going to be our constant for this reaction. Okay, so we're going to go ahead and look at second order reactions here. Obviously we have a differential rate law here that's second order because our exponent tells us. Now the integrated rate law for a second order reaction is going to have this formula. So guys, please make sure that you memorize this. Some things to note about this is that obviously your concentration is going to be related to your time. There is a dependent property there. And I want you guys to notice something else, okay? So remember on the last slide, we utilized the concentrations and time, and we took the natural log of those concentrations and graphed it versus time, and we got a straight line with a negative slope, and that helps us to determine that we had a first order reaction. Now, in this context, when we do that, obviously you see that we do not get that straight line, okay? And so what that tells us is that the reaction that we're looking at for this specific process is not first order, okay? Now Now that we know the equation for the second order integrated rate law, we can go ahead and try that as an option. So again, we're going to utilize the y equals mx plus b approach. Our y is going to correspond to this portion of our equation, while of course our slope is going to correspond to the m and our time is going to correspond to the x. So in this case, if we have a second order reaction, we are going to be getting a straight line from the graphing of 1 over our concentration versus time. And in this case, what we get is a straight line. Now notice that the straight line has a positive slope for our K value, which is what we would expect for this specific type of reaction. Okay, so this is in fact a first order reaction because we get a equation with a positive slope after graphing 1 over our concentration versus time. Now, also, all the other things apply in terms of being able to plug in concentrations and manipulating this equation to solve for our time value, or we could use our time value and one of our known concentration values to subsequently figure out our concentration at a specific time. So basically, we can manipulate and utilize this equation in a very similar way to what we did with our first order integrated rate law, okay? But obviously, we need to follow a different equation when we're dealing with second order reactions. So zero order rate laws are basically kind of rare. Most reactions are not going to have a zero order rate law. And the zero order rate law, the differential looks like this. And as you can see, when we convert this into the integrated rate law, we get this equation here. Okay. And basically something to know about this is that this is the type of kinetics seen when enzymes are present. It's very common there. So things to note about zero order rate laws, basically it doesn't depend on concentration. Okay, so what do I mean by that? Well, the rate of your reaction for, say, a first order reaction, as you can see, as the concentration changes, the rate of your reaction is also going to change, right? Okay, so as time progresses, this line kind of flattens out because the rate of the reaction is actually dependent on the concentration of your reactants. Okay, in the case of zero order zero order reactions, okay, the concentration doesn't affect the rate. Okay, so if you plot a concentration of reactant versus time plot, and you basically get a straight line with a negative slope, you subsequently know that you have a zero order rate law. So none of these equations are going to be provided for you. It's going to be assumed that you know what they are, and for each of the three types, the first, second, and zero order rate laws, you guys need to be able to differentiate between the integrated rate law and the differential rate laws. Okay, so when you're asked for them, please make sure that you write the appropriate equation. Okay, so make sure that you guys are spending a little time memorizing them. Also, please consider and spend some time with the graphs. Okay, we want to be looking at, what are we graphing versus time? Okay, in order to get our specific slope, what kind of slope do we need, and what does it tell us about that specific reaction? So memorize the formulas, guys. Get familiar with the graphing procedures and the signs of the slopes that are anticipated for first, second, and zeroth order reactions.